Section 1-2, domain and range. Now, who remembers something about domain and range? You remember hearing those words before? Do you remember what they mean? We actually used them. Actually, we didn't use them in the last class, but we talked a lot about input and output, right? In the last lesson. Well, domain and range is very related to input and output because all the values that are in the input, that's your domain. So like all those x's that we could put into a problem, that's your domain. All the output values, that makes up the range. So that's our input and output values. The domain is the set of all the possible input values to a function. And a lot of times we can use anything we want. There are a few times where there are some limitations, and we'll talk about those as well. And then, as I mentioned, the range is the set of the possible output values of a function. So the domain is just all those input values. Usually we call those x's. The range is all those output values, and usually we call those y's. Example 1, using the tree table shown. Oh. Okay, so it's a table about trees. I don't really think it's a tree table, but anyway, tree table shown, determine a reasonable domain and range. So when we look at this, the independent variable here is the C value. And a lot of times, most of the time, they'll put that on the top. But C is your input value or your independent. So C is the input. And that means H is the output. So in other words, if you think about what this is saying, they're saying the circumference of a tree, which means the distance around the tree, around the trunk, changes. And so then the height of the tree changes. So the idea is here, as the tree gets bigger and further around, it's also getting taller. And they've made a table to kind of represent this. It looks like it's probably just one tree that they measured. So the question is, what is a reasonable domain? And let's start with that, a reasonable domain. And when we talk about reasonable, we're talking about what could happen. So just to think about this a little bit, would it ever be possible for our circumference to be a negative number, for instance? Would that make sense? Could the circumference of a tree be a negative number? No, circumference can't be negative because that's the distance around a tree. Distance is always positive, right? Could the circumference be a 0? Is it possible that the tree, if there's a tree there, that its circumference is 0? No, because again, that would mean there's nothing to go around. Okay, so we can't have negatives. We can't have 0. But really, I mean, look at the numbers we've got. 1.7, 2.5, 5.5, 8.2, 13.7. Couldn't it really be anything that wasn't negative or 0? Right? At least on the bottom side. So we would start out by saying, okay, let's say it this way. Let's say, I'm getting my classes confused and I can't remember what we've talked about. But let's say that C has to be greater than 0. Does that make sense? If that's what that says, 0 is less than C or C is greater than 0. Now, again, we're determining a reasonable domain and range. We don't know what kind of tree this is. They didn't tell us. But what do you think might be a reasonable circumference? How big could a tree get? And some of them actually get pretty big. I don't know. Has anybody heard about like the big sequoias or the big redwood trees in California that like they can cut in the middle and cars can drive through them and stuff? So, and I don't even know what units we have here. So I think what we're going to do is we're going to make it really easy, and we're just going to say that C has to be greater than 0. We don't know how big this tree could get as far as circumference. Now, I'm sure there is a limit, but for us to be able to guess what it is without knowing what kind of tree or anything is probably, or what the units are, since they didn't even give us the units, is a little bit tough. So we're going to say our domain is going to be the values that are greater than 0. And we're going to talk about how to write that in a little bit. What about our output, the height? So the range. Well, again, if we think about it, could our height be negative? No, not if there's a tree there. Could our height be 0? No. So again, isn't it going to be, and we don't know how tall it's going to get. So again, isn't it going to be like the height has to be greater than 0? Does that make sense? If you've got a tree, and again, they didn't tell us the units, so we don't know if it's feet or inches or whatever, but we're going to say the height is greater than 0. Now, I'm going to mention this right now because we're going to be talking about it in a second anyway. There's 2 different ways that we can write this. Now, we just wrote it as an inequality, right? C is greater than 0, H is greater than 0. But usually when we write these things, in fact, let me take this and move this down here so that I have a little bit more space. So usually when we write these things, we're going to write them in one of 2 ways. We're going to write them in what is called set notation, or we're going to write them in what is called interval notation. If you look at that box underneath there, that's what that's talking about. So let's start with set notation. Set notation, when we talk about sets, we always use these little braces. That's called a brace. So that tells us we're talking about a set or a group. So here's how we write set notation. We always take our variable that we're talking about and we put that in there first. And I'll tell you how we say it in a minute, but this is how we write it. So we're going to put that variable in, the C, and then we put this vertical line. And after that, we just copy down what we figured out. C has to be greater than 0. And then we close our brace. Put the other brace there. So here's what that means. This is how we would say it. It's the set, braces, it's the set of all the C values. And then technically this line means such that. It means there's a condition. So the set of all C values such that C is greater than 0. So that's one way we would describe our domain. And let's go down here and let's do the same thing down here with set notation. So how would we do this one? We'd write our brace. And then what's the variable that we're using there? H. So we would write down the H. And then again, we'd put our line. And then what was the limitation we came up for that one? Came up with for that one? Well, we just copy this, right? H is greater than 0. And then we close our brace. So again, the way we'd say that is, it's the set of all the heights, the H values, such that H is greater than 0. That's our range. Okay. Now, the other way of writing it, these things, is what we call interval notation. Interval notation. And interval notation is much shorter to write, typically. And so what you do in interval notation is you just talk about the beginning of the interval and the end of the interval. So what's the lowest value that we were talking about here when we were looking at this domain? The lowest value is 0. So we write down a 0 and then a comma. And then what was the highest value we were talking about? Well, we didn't come up with the highest value. So again, without any more information other than what they gave us in the problem, we would say it just keeps going forever. And when it goes forever like that, we put in this symbol right here. Does anybody remember what that symbol means? Infinity, right? So that means it keeps going on forever. Now, the other thing after we write down those endpoints that we have to think about when we do interval notation is, are the endpoints included or not included in the interval? So notice this one we said C is greater than 0. So was 0 included in the interval, in the set? If C is greater than 0, was 0 part of our interval? No, because we said it can't have a circumference of 0 and it can't have a height of 0. So 0 is not included. So if that endpoint, in this case 0, is not included, it gets parentheses. Now, here's maybe a little bit of a trick question. Is infinity a number? No, it's a concept of increasing forever and ever and ever. So could this non-number ever be included in our interval? No. So that automatically, infinities always get parentheses because it's not a number that can be included. Okay. So if we go down to the range here, interval, What do you think the range will look like if we do it in interval notation? And again, that's kind of a trick question. What's the lowest value in our interval that we consider? 0. And do we have a highest number? No, it just keeps going forever. And was the 0 included according to our inequality statement? No, so that's going to get parentheses. And then infinity, remember, can never actually be included because it doesn't ever stop. And so that gets parentheses also. Now, everything was parentheses there. The other option is, if the endpoint is included, we would use a bracket instead of parentheses. That would tell us that if we put it on the 0, that would tell us, oh, this 0 is included in the interval that we're talking about. Okay, so that didn't happen with this one, but when we get to that table that you're going to see in just a second, or that you already see on your paper, that's what we're going to be looking at. So let's try this one. The population of a small town in the year 1960 was 100 people. Since then, the population has grown to 1,400 people, reported during the 2010 census. Choose descriptive variables for your input and output and use interval notation to write the domain and range. So the first question is, if you're looking at this problem, what do you think the input would be? What words or word would you use to describe the input? Say that again. The year. But in the year 2000, or in the year 1960, I should say, this was the population. In the year 1970, they could find the population. In the year 1980, they could find it. So yeah, your input is the years, or is the year that it is. And so then what is the output? I just gave that away, didn't I? The population. I'm going to abbreviate. All right. So what letter, because they asked us to choose descriptive variables, what letter would you guys like to choose to represent the input? And there's no right or wrong answer. You just have to pick one. Y for year. Okay. And you may see sometimes time for T. That gets used a lot in math. And then what descriptive variable would you like to use for the output? And again, there's no wrong answer. We just have to pick something. P. And a lot of times we do want to pick things that make sense, right? Y for year, P for population. Okay, so once we've done that, we want to use interval notation to write the domain and range. So this time we were given specific values, right? So what is our, and we're using interval notation. So that's the one where we talk about the endpoints, right? So let's do the year first. What is the lowest year that we were talking about here? 1960 was the earliest year that we were talking about. So we put our comma, and then what was the biggest year that we were talking about? 2010. Now, once we see that, the other part of the question is, using interval notation, is the 1960 going to be included in the interval, and is the 2010 going to be included in the interval or not? And one could be included and one not. We just have to figure that out. So does it seem like the 1960 is included, should be included in the interval from this information that they gave us? Yes, because they said in 1960. When Y was 1960, the population was 100, right? So since it's included, that's where we use a bracket. Okay. What about the year 2010? Should that be included? Yeah, because they said in 2020 or 2010, the population was 1,400. So that's our interval for the domain, the inputs. Now let's go to the outputs, the population. And again, we want to talk about the ends. What is the smallest value we have for the output that we know of? 100. Okay. And then what is the biggest value that we know of for the output? 1,400. Is everybody okay with those two numbers? Okay. And then are these values included or not included? What about the 100? Included or not included in our range? Included, because they said this is the population. So yes, the 100 is included in the range. And how about the 1400? Also included. So in this problem, unlike the last one, all of our endpoints for interval notation were included. So they all got brackets. Okay, and we'll do some more practice with that as time goes on. So we've already talked about this, but let's take a look at our notation. The first one is called set builder notation or just set notation. And we went through this, like I said, in that first example, but this is saying you're talking about the set of x values, right? The set of x values. And this line means such that, and then they give you the description, the condition that we have to have met. So the set of x values such that, and the way I would say this is 10 is between, or sorry, 10, x is between 10 and 30, including the 10, but not including the 30. Or you could just read it exactly as it looks. The set of x's such that 10 is less than or equal to x, which is less than 30. That's another way to read it as well. And then interval notation, which is the one we've been working with here recently, we deal with the endpoints of the interval, we list those, and then we use parentheses for what we call open endpoints. That means they're not included. So the parentheses are for open endpoints. That means they're not included in the interval. And we use brackets for what are called closed endpoints, and that means they are included in the interval. So if we go back to this one right here, do you see that this is 10 is less than or equal to the x? So the 10 is included in the interval. And notice what we have here. We have a bracket. That's because the 10 is included in the interval. So this is why this is a bracket. Because of the, I should circle maybe just the bottom, the or equal to part. And then for the other one, notice the 30. Is the 30 included in the interval? If it says just less than 30, no, it's everything up to 30, but not including it. So that's why this one gets parentheses. So we've done some practice with that. You've maybe seen, I know you've seen the inequality signs before, depending on what class you took last year. You may or may not have seen the interval notation. But that's two different methods that we want to be able to use in order to describe our intervals, our sets. Okay, so again, here's just some different examples. Something to notice here, and I'm going to point it out a couple times. Notice every time there's not an equal sign on your interval, that always means you're going to have over here, you're going to have parentheses. Okay, every time there's not an or equal to sign, you're going to have parentheses because that means it's an open endpoint. Every time you have the equal to sign, that means you're going to get a bracket. Okay. Now, the other one that we also talked about in that very first example was anytime you have some sort of an infinity, it's always parentheses. Because infinity is not a number, so it can't be included in the interval. It's that concept, like you mentioned, it's that concept of either increasing or decreasing without bound, without a boundary. Notice the really easy thing here. What do you notice about all of these inside parts of the set notation? They match up exactly with the inequality that we've got, right? So that's really not hard to convert from an inequality to set notation. You just put the variable in the front with the line, and then you write it down with the braces. Okay. Now here's the one that you're laughing at. All right. So if we are trying to describe all real numbers, now over here, that's pretty easy from negative infinity to positive infinity, right? Here's what this one means. And I've never really seen it like this, and maybe I just forgot to fix it, but usually you have the braces on the end also. Here's what this means. You're talking about all the h's, and then here's an h, And so here's what these two symbols are that you were laughing about mean. Anybody recognize that symbol? Seen it in the past? That symbol means is an element of. That means it's part of the group. Okay, so like when we talk about sets, each of you guys would be considered elements of the college algebra class. You're part of the group. Okay, so that's what that means. H is an element of, and then this special. I know some of you have seen this symbol before. What does that symbol mean? That means real number. Yeah, all real numbers. So this is saying that H is an element of the real numbers. That's set. So they're just, again, they're describing the words in a symbol form. So that's, I tend to use that one a lot. So those who have had me in the past, I guess that's just Addie from this class. But you've seen that symbol because I don't like to write out all real numbers, so I abbreviate. And that's the abbreviation for all real numbers. To combine two intervals together, because sometimes we're talking about more than just one interval, right? Maybe we've got two intervals that are put together, or even 3 or 4, or whatever. So to combine two intervals together, if we're using inequalities or set builder notation, remember those are almost identical, we just use the word or in between the intervals. So for instance, we might say, well, let me draw a picture. I'll draw a picture. So we've got a number line, and we've got a -2 and a +5, and this one is a filled-in circle going this way. This one is an open circle going this way. So let's review a little bit. How would we describe this left-hand side using an inequality statement? What would we say? And we'll say that our variable is x. So what would we say about x if we're talking about this left-hand side? Correct. X is less than -2, and we know it's just less than because of the open circle, right? That's why I call it an open endpoint. And then how would we describe this one? X is greater than or equal to 5. Does everybody remember that from their previous math classes? So if I want to put those two groups together, what we say is, we'd say, okay, we're talking about the x's such that x is less than -2 or x is greater than or equal to 5. So all you do is you take your two statements and put an or in between them if you want to put the two groups together. Okay. And I think you've done that before. You would have done that in Algebra 2. But using interval notation, we use a slightly different notation here. So here's what we do for that one. We use what is called the union symbol. It means we're going to take two groups and combine them together. Like a union of two things, you put two things together. So here's what we would do. How would we, let's use a different color here. How would we describe this on the number line using interval notation? And I guess we haven't done one like this yet, so this will be a good question. In this case, we don't know the lower boundary, right? We do know the upper boundary. So let's start with comma, and our upper boundary is -2. Does that make sense? And should that get a parentheses or a bracket according to what we've learned? Parentheses because it's open, right? Now, this is that idea of we're going forever to the left, right? Forever bigger and bigger negative numbers. So what do you think might go as the lower boundary here before the -2? Negative infinity. If we want to go forever to the left, and then that always gets parentheses, so we would put that in. Okay, so then how do you think we do this one? What's the lower boundary this time? The 5. And then the upper boundary? Well, there isn't one, so we say infinity. Now, should the 5 get parentheses or brackets? Bracket, because it is or equal to, and it's a closed interval. And then the infinity, parentheses, always parentheses. Okay, so that's how we would describe that one. If we want to put them together, we would say negative infinity, comma comma -2 with parentheses. And then we would put this union symbol, which is like a, well, that's deformed because my smartboard had a problem there. But anyway, it looks like a big capital U, basically is what it looks like. And then we would put the other one, 5 to infinity, parentheses. So that would be how we would put the two groups together if we're using interval notation. All right. So does that make sense, kind of how they're similar, but they have some differences to them? And like I say, I know the interval notation for probably most of you is a little bit new, but it's not too difficult. You just have to remember the lower boundary and the upper boundary idea. Describe the intervals of the values shown on the line graph below using set builder and interval notation. All right. So which one do you guys want to do first? I'll be honest, when I say things like this first part, the 1 to 3, I think interval notation is really easy for that, right? Because what do we write down? The lower boundary is 1 and the upper boundary is 3. So we just write that down. And then according to the circles, they're both filled in. Should we have brackets or parentheses? Brackets, because they're both closed. So bracket here, bracket here. And then since we've got another interval to look at, we put that union symbol, right? And then what's our lower boundary this time? And then it goes forever, so our upper boundary is not existent, so we have goes to infinity. Now, the 5 has an open circle, which means what sort of a symbol should we put in front of it? Parentheses. And then infinity always gets parentheses. So that's how we would do this in interval notation. Let's try set notation. Now, what do we know about set notation? We always start out with the brace, right? And let's just say again that we're using x's. So we really always start out with this every time, unless it's a different letter and then we use a different letter. But does that make sense that every time we start out with that? Now, we've got two different intervals. We're going to have an or in between them. How do we describe this first one using an inequality? Okay. And we usually put the 1 first, right? And we would say it that way. So 1 is less than or equal to x, and then what else is true about that first interval? Yeah, x is less than or equal to 3. So that's the first interval. It has endpoints, so x is between those two. And we put the or equal to on because they're both closed. And then we said, okay, we need an or. And then how do we describe that second one? X is greater than 5. I actually blew that one because that's the example I used on the previous slide when I was making something up. Okay, and then that's the end of our set. So anything that fits into either of those groups is part of the set. So we've talked about how we can look at numbers. Now we want to talk about domain and range from graphs. Since the domain is the set of the possible input values to a function, this corresponds with the x values from our graph, because the x values we typically use for the inputs. And then since the range is the set of the possible output values to a function, that corresponds with the y values on the graph. So the x's are talking about left and right. The y's are talking about up and down. So here is a picture. All right. So determine the domain and range of the graph below. So let's start with domain. And remember, domain is dealing with left and right. That's the x's, correct? In this case, they don't have any specific values, but we're going to assume that it's the left and right stuff because that would be where the x's go. What is the lowest x value that we have in this picture? 1975, right? Right here at the beginning. So I'm going to go ahead and use interval notation. I'm going to put 1975 first. And then what is the highest value that we have? Now we have to be careful here because they're going by 5s. So what would the highest value be here? So each of these little blocks is going by 1s. I would have said 2010, but it's really what? 2008. You're trying to trick me. Okay, so 2008. Is everybody okay with that? Because there's only 3 little blocks past the 2005. Since there are no open circles, we get to assume that they're closed endpoints. So what sort of grouping symbols will we put there? Parentheses or brackets? Brackets, because if it's closed, it's always brackets. So unless you see open circles, you get to assume that it's closed. Or unless it tells you that it's open. So that would be our domain, 1975 to the year 2008. What about the range? Okay, well, range, we're using the y values, right? So up and down. So the question is, what's the lowest y value that we see? And we may have to estimate because these are not listed as clearly. So do we see that the lowest y value is right down here somewhere? Well, since you both said 190, we'll go with 190. It might be lower than that, but you know, we're estimating, right? That's what estimation is. So then the other question, where else do we have to look? The highest value, right? The highest value up here somewhere, which is slightly above 2000, it looks like. So if somebody wants to estimate that one for us. 2010. All right. We like those 10s. 2010. And again, since we don't see any open circles, we get to assume closed interval. So the production went down to a certain value and then it went up to a certain value. And so what sort of grouping symbols do we get here? Brackets. And again, we're estimating from the graph, but that's the idea. We can look at the x values, which is left and right, and talk about the domain. We can look at the y values, which is up and down, and talk about the range. So again, we'll talk about domain and range. What do you guys think about the domain? I think we've got probably 1952 as the first one. I mean, you'd have to get up here and look pretty closely, but I think it's 1952. Okay, and then how high does our range go? Well, that one is, I think it's 2002. That one is really tough because it's so far away. All right, so what happens there? Do we see any open circles? So what does that tell us about our grouping symbols on the ends? Both will be brackets, that's right. Okay, and how about the range? I think 40. Yeah, it looks like it comes down and just touches that 40. So 40 is our lowest value. And then what is our highest value? This will be a lot tougher to try and estimate. Well, 90 is up here. So like, 88, something like, because this is going by, must be 2, 4, 6, 8. 2, 4, 6, 8, 10. So yeah, I think 88. I think you guys said that, right? And I would agree with that. Again, no open circles. So what would we say about the endpoints? Brackets. All right. So if you want to, you can flip back to your notes from yesterday or from section 1.1, and we're going to talk about each of these toolkit functions. Depending on how much time we have, we've got 10 minutes, so I think we'll get through them. We're going to talk about the domain and range for each of these toolkit functions. So you can write on that paper if you want to. If you don't want to, that's fine. But we're going to talk about the domain and range of each of these functions. Okay? So looking at our first one, which remember was the constant function, a horizontal line, what do you think the domain is? And notice we do have arrows here. What's the domain of a constant function? All real numbers, right? You could say negative infinity to positive infinity. I think I've got it here. Oh, I hope I don't have both of them at once. I'm going to give this away. Well, before we go on, what is the range if this is your function? F of x equals c. I mean, if it was actually this one, it'd be 2, right? 2 is the entire range because it's always 2. If it's some other random c value, then it would be just c. So let's see what I've got here. So our domain is everything from negative infinity to positive infinity because it's all real numbers. And then our range is only this one point. So its lower boundary and its upper boundary are the same. So we just write c. And the c is included. So that's the constant function. All right, let's look at the identity function. What do you think the domain would be this time? Yeah, it keeps going. I mean, we don't see it, but it keeps going down and forever to the left. Keeps going up and forever to the right. So it keeps going left and right forever. The domain is negative infinity to positive infinity. It's all real numbers. What about the range? The up and down part. Also all real numbers, right? Because it goes down forever on the left and up forever on the right. So actually both of those ends up being all real numbers. And we'll find out actually a lot of our domains are all real numbers because that allows us to do a whole bunch of things with whatever numbers we want to. Absolute value. So what do we think about the domain this time? All real number. Doesn't it go left and right forever? But what about the range? The range is limited. Now think about the graph. Think about what we were just doing on those last pictures, the graphs. We always identified the lowest first and the highest, right? What's the lowest on this one? 0. It doesn't ever go past a y value of 0. And then how far up does it go? It goes up forever, right? Up and to the left and up and to the right. So our domain, all real numbers, negative infinity to positive infinity. And the range, there's no open circle, so it includes the 0. And then it goes up forever. What about this one? Quadratic. What do we think about the domain this time? Yeah, doesn't it go left and right forever? And then what about the range this time? Same as the last one, wasn't it? From 0 to infinity. So that's really easy for me to do because I can just copy and paste because they're identical as far as the domain and range. Now they obviously look different, but their domains are the same and their ranges are the same. So now the cubic function, what about the domain here? The left and right stuff. Yeah, when you've got these arrows, that means it goes forever somewhere, right? So this is, it looks like it's going down, but as it's going down, it keeps moving to the left further and further and further. So the further down you go, the further to the left you go, it goes forever to the left, and then the same thing happens to the right. So all real numbers. What about range, up and down? All real numbers again, right? Because it's going up and down forever. So both of those, negative infinity to positive infinity. And again, just to emphasize, infinities are always parentheses. Every time you use an infinity as an endpoint, that gets parentheses. How about the reciprocal function? Now this one's a little bit different. So the reciprocal function, what do we think about the domain this time? Does it go forever to the left? Yes. Does it go forever to the right? Yes. But you'll notice right here in the middle, there's no value when x is 0, is there? So that means we can go from negative infinity to 0, and then from 0 to positive infinity, but the 0 is not included. So remember what that's going to look like? You're going to have parentheses by the 0 because it's not included. And then with a union because you've got two separate areas. Okay. And then what about the range? Does it go down forever? Yeah, right here. Does it go up forever? Yeah. But again, look at what happens right here. Does it ever hit 0? No. So look at, this is how we would write that. With our union symbol in between, they actually end up being the same numbers. So from negative infinity to 0, union with 0 to infinity, and that's for both of those. All right, next one, the reciprocal squared function looks like this. What do we think about the domain? We just have to get rid of the 0 again, right? So that's going to be the same as the last one. What about the range? It actually doesn't ever quite hit 0. If you've got 1 divided by something, even if that something is squared, it's never going to actually equal 0. So that's where you're going to have from 0 to infinity, but instead of a bracket, you're going to have a parentheses on that one. It's hard to tell because it looks like it touches with these lines, right? They get as close as you want to get, but it never actually touches the 0. Even 1 divided by 100 trillion is still not quite 0. Last two, the square root function. We can see, and we've talked about this in the past, right? You can't take the square root of a negative number. So where do we have to start? 0, and then to the right, so 0 to infinity. Same thing happens actually with the range. The lowest value is 0, and it goes up from there. So it goes up slowly, but it still goes up forever. So 0 to infinity, including the 0 on both of those. And then our last one, what do you think about this one? Does it go left forever? Does it go right forever? Is there anything missing in the middle? No, so all real numbers for domain. And then how about up and down? It goes down forever and up forever, just slowly, right? So this one again is going to be that negative infinity to positive infinity for both the domain and the range. We've just finished up with all those different graphs and talking about the domain and range of all those basic toolkit functions. If you remember back to your Algebra 2 days, they're using f of x equals the square root of x as the parent function here, and they've done something to it. Do you remember what happens when we take a function and add a 4 to the x? What does that do to the graph of the function? Remember, when you affect the x, you're always affecting something left and right. You're affecting something left and right because that's what x's control is, left and right. If you're not affecting the x and it's on the outside, then you're affecting something up and down. And also, if you remember, if you're affecting the x, it always works backwards of what you'd think. So adding 4 actually moves this graph to the left 4 spaces. So if you remember your toolkit function for this one, it looks like this. So if we move it to the left 4 spaces, it's going to look like 1, 2, 3, 4, and it's going to look something like this. So that's the first piece. That's the +4. What does the 2, when you multiply by a function by 2, and it's on the outside now, so it's not affecting the x anymore. It's affecting up and down stuff. Does anybody remember that one? And it's been a long time since you did this. So what happens there is when you multiply by a 2 on the outside, and it affects up and down, you're stretching the function by 2 because every value that this first function gives you gets multiplied by 2. So it just takes this thing and it stretches it so it's going to look more like that, which to us doesn't really change the domain and range at all because it's still going up and it's still going to the right, so no big deal. But once we see that and we know that we're starting here and then we're going in those directions, let's think about our domain. What is the domain that we would have for this function? And there's actually a couple ways. I'm showing you a graphical way to do it, like thinking about the graph. But what's the, and we looked at these before, what's the lowest value? What's the furthest to the left value that we have on this graph? -4, like on the pictures when we would look to the left. So -4 is the lowest, and we see there's no highest value, right? It just keeps going to the right forever. So we would say infinity. And we know infinities always get parentheses, so that's, you don't even have to guess on that. But what do we have to know about the -4? Is that going to be a parentheses like the infinity, or is it going to be a bracket? And how do we know? It is a bracket because it's closed. Is it okay to put a -4 into this equation? Yeah, -4 + 4 is 0. And what is the square root of 0? Well, it's 0. 0 times 0 is 0, right? That's the smallest number you can take the absolute value or the square root of. So we get our domain is from -4 to infinity. Now, what about the range? And remember, range is the y's, so it's going up and down. What's the lowest value that we have for the y's? 0. And then doesn't it keep going up forever? I mean, slowly, slower and slower, but it keeps going up forever. So that's going to be an infinity. Infinity always gets parentheses. What about the 0 this time? Will it get parentheses or brackets? It is bracket, okay? Because that's your boundary point. So if it's a filled in circle, bracket. That's our graph, a little bit nicer one than what I drew. And then we get our domain and range down here. This one is a bit trickier, but can we figure out what family this one is in? We're not going to try and do it by hand, but can we figure out what family at least this is in? Which one of those toolkit functions is this related to? And it may not be super duper obvious, but hopefully by kind of examining, you might be able to figure it out. It is. It's in the reciprocal family. So I think I have a picture of that right here. Yep, here it is. And you can see it's been moved over to the right a little bit because our reciprocal function is over here like this, right? And it also got flipped because the higher part is on the left now and the lower part's on the right. So not that that matters a whole lot, because what we're interested in is what is the domain and what is the range. So let's start out with domain. That's the x values. Well, what is the lowest x value? And again, I don't have arrows on these, but the graph keeps going to the left and to the right, just like the reciprocal function does. So what's the lowest x value? Yeah, it just keeps going forever to the left, right? So our lowest value is negative infinity. What's our highest value? How far to the right does it go? Forever to the right. Now, we do have a problem though. Where is the problem as far as the x values? Do you see how there's this spot right here in the middle where the blue line goes up on one side and it goes down on the other side, or the blue curve, and there's no value when x equals 2? If you look at this equation, do you see that there's a problem if x equals 2? This would be 6 minus 6. And so there'd be 3 divided by 0. And remember, in math, we cannot divide by 0. Actually, you can, not even if it's not math, you can't divide by 0. You just can't do it. Okay? So we can go all the way from negative infinity to negative 2. And then you're right, you said there's a u. And we can go from 2 then all the way to infinity. And we've already talked about this. We know the infinities have parentheses. What happens on this 2 on either side of this? They're not included because you can't include the 2. That's the whole point. So we need to use parentheses on each one of these. When it jumps like this from being up and then all of a sudden is down, that means there's something in between there that is causing a break in the graph. And we have to take that out. So how about the range? What's the lowest y value and the highest y value? I mean, do we see it goes down forever and also goes up forever? So it's going to be kind of similar because it still doesn't connect, does it? But where's the break this time? 0. That's the spot where where it gets cut, I guess. It's one way to think about it. So we put that 0 in here and the 0 in here. And again, we're not including the 0, and then we combine the 2 with the union. Now, this is one case where, to me, interval notation is actually harder than set notation or set builder notation, because all we would have to do in set builder notation in this one is we could say the domain is all the x's such that x does not equal 2. You can just throw that one number out and you're done. And then the same thing down here. How could we write this one? Well, I guess we're saying g of x here such that g of x does not equal 0. Just throwing out that one number. So that's 2 possibilities. I think this book will probably, we probably focus on this in this class, but you do have that other option because we did talk about both the set builder notation and the interval notation. We got to talk about our piecewise functions. Okay, this is in your notes, right? Or is it not in there? Okay, a piecewise function is a function in which the formula used depends on the domain that the input lies in. In other words, you take a bunch of different functions and you piece them together to make one big function. Okay, so we notate this idea like this. You're going to have f of x. This is the one big function. And then you've got one little equation in there. And that equation is used if the input value is in a certain domain. And they're going to tell you what domain. It might be like x is less than 5 or whatever. But they'll tell you if the x value you're putting in fits into this group, the red group that I've underlined here, then you use this top formula. And then you're going to have another formula. And then you use that formula if the input is in the domain for that second formula. And again, they'll list those domains for you. And they can't overlap, so there's no question of which one you should use. And then you'll go to the third one, or however many there are. There could be 2, there could be 7. And you've got your third formula, and you use that one if the input fits into that group, that statement. So that's the idea, and it'll probably be easier when you see an example. So let's take a look at this first example. So a museum charges $5 per person for a guided tour with a group of 1 to 9 people, or a fixed $50 fee for 10 or more people in the group. Set up a function relating the number of people n to the cost c. So our idea is that we're going to have the cost based on the number of people. That's how I'm going to name our function c of n. And do you understand we have 2 cases? We've got one case, one way of calculating the cost if there's between 1 and 9 people. Then there's another way of calculating the cost if there's 10 or more people. Okay, so let's start with the first sentence they gave us. A museum charges $5 per person for a guided tour with a group of 1 to 9 people. So if it's $5 per people and there's n number of people, excuse me, what equation could you use to figure out the cost? 5 times n? Because, right, if there's 5 people, it'd be 5 times 5. If there's 8 people, it'd be 5 times 8. $40. If there's just 2 people, it'd be 5 times 2. Okay. Now, we'd say, okay, so we use this formula, 5 times n, if there's different ways to say this, but we'll just say it this way. It says between 1 and 9 people. So we're just going to say that's how we would write between 1 and 9 people. Okay, from 1 to 9. Now, obviously, there's an assumption here that you can't have half people running around and quarter people running around and things like that, but we're just going to say n is between 1 and 9. The context of the problem says that they're all integers. What's the other option for figuring out how much it costs? Well, that's the second one, right? Second part of the sentence. What does that tell us? What equation would we come up for the cost there? It's actually not even an equation. They just tell us it's going to be $50 if what is true. So we could say if n is, how would we write that in our symbols? Greater than or equal to? So in other words, if you bring 50 people, you're still only going to pay $50 because that's what they said, right? Anything 10 or more, you just pay the flat fee of $50. So that is an example where a piecewise function would be used to calculate a cost in this particular case. This used to happen a lot with, previously used to happen a lot with cell phones. It probably doesn't anymore because a lot of people get unlimited everything, seems like. But let's say that you had a cell phone, like my cell phone right now. I get unlimited calling and unlimited texts, but I get 5 gigabytes of data per month. Okay. And as long as I only use that 5 gigabytes of data or less, I pay a certain fee. But what happens, and you guys probably know this, what happens if I go over that 5 gigabytes of data? Well, yeah, actually there's tricks. Sometimes they just slow it down, but in mine they actually cut it off. So if I want more, I have to pay for more. So that would be another situation where that's a piecewise function. As long as I stay less than 5 gigabytes, I pay this price. If I go more than 5 gigabytes, then I have a new formula that they start plugging me into because I'm going to pay for extra data. Does that make sense? Yeah, and some you're right. Some you still get more and more data, but it's just slower. But it just depends. Okay, so this happens a lot in life. So let's take a look at this one. Cell phone company. Okay, so here's an example. I guess here's almost exactly the example we were looking at. Cell phone company uses the function below to determine the cost C in dollars for G gigabytes of data transfer. So find the cost of using 1.5 gigabytes. Well, notice here are the 2 domains. The question is, are we using between 0 and 2 gigabytes of data, or are we using more than 2 gigabytes of data? Does that make sense from those domains if that's what they're saying? So for this person, they're paying $25 a month as long as they use less than 2 gigabytes of data. If they use more than 2 gigabytes of data, then they have to be bumped up into this different equation. Okay, so let's take a look. For this first one, how much is this person going to pay if they use 1.5 gigabytes of data? Which domain are they in? The red one or the green one? The red one. Does that make sense? Because 1.5 is between 0 and 2. So we would say C of 1.5 is equal to 25, because we use that. It's just set, $25. Then what about C of 4? Which domain is that one in, red one or green one? The green. Now this one requires more work, right? Because that means we have to take 25, which makes sense. You have to pay 25 no matter what, plus $10. Evidently, they're paying $10 for each additional gigabyte, 4 minus 2. So how many additional gigabytes are they using? Well, that's the 4 minus 2, right? They had already paid for 2. So if they use 4, they're having to pay for 2 extra, right? So doing that work, 25 plus 10 times 2, that's the 2 extra, and that'd end up being $45. So that person has to pay $10 per gigabyte of extra data that they use with their particular cell phone company. Evidently, they get to keep their speed, but have to pay a lot more, almost twice as much. I think this is our last one. We're going to graph this one, and we are going to graph this piecewise function. Notice it has 3 parts. Now, I have a way that I like to do this, and I'll just show you that if I can. I really need a 3rd color or a 4th color. Okay, so notice there are some dividing lines in our piecewise function, right? Do we see that this one switches from one function to another at x equals 1? Does that make sense? The top function is for x is less than 1, less than or equal to 1, and then the middle one is x is equal to, or x is greater than 1. So there's one split in the function, and what I'll usually do is maybe just put a dashed line here, whoops, crooked dashed line, to say, okay, this is one spot where our graph is going to get split. Where's the other spot where the graph is going to be split? When x is 2, right here. Okay, that's where that one splits from the middle one to the bottom one. So I might put another mark there. Those are pretty close together. I need to maybe spread them apart further. Okay, now once I've got that figured out, and again, we do this in Algebra 2. We've done it in some other classes, advanced math if you took that one. So we get to choose x values, and we're going to get our f of x values out. But we have 3 different functions to work with. We just have to make sure we choose good values that are in each of these correct domains. So our first domain is, for the top one, we need less than or equal to 1. And actually what I usually do is I put my dotted line in here to separate the 3 functions. And I've got 1 as a boundary, and I've got 2 as a boundary. Okay, now I know this is odd because usually in a T chart, we don't put any number in multiple times, right? But the idea is we need to know where each of those boundaries ends up based on each separate function. So I'm going to show you how that works. All right, so the first one, we need numbers that are less than 1. So like 1, 0, and -1. So let's put those in. And according to our function, we're using, I'm going to go ahead and use red. We're going to use red here. So this is the red function. So this is -1 squared. That's 1. 0 squared is 0. And then 1 squared is 1. So that function looks like this. -1, 1, 0, 0, and then this. Now, this one right here, we want to think about. Do you remember the open and closed circle idea? What does it mean if this is a less than or equal to? Should my circle there be open or closed when x is 1? Closed. For this top function, it's closed. So this is going to be a closed circle. And then do we recognize this function, x squared? from our toolkit functions? It's a parabola, right? So we have to stop at the green line there, but on this side, it just keeps going, and it's a parabola going up like that. But once we hit the green line, we've got to stop, because this function stops when x is 1. All right, I'm going to use green for this next one. And since I don't have any other values, I'm going to put in a decimal number. So now using the middle function, what is the value of this function if we plugged in a 1? Now, I know technically we can't put in a 1, but again, we need to know where the boundary is. So we're allowed to put in the 1 anyway, even though it says just greater than 1. So if we put in a 1 to this middle function, what's the value going to be? And don't make it hard, because it's really easy. 3. It never changes. The x value doesn't matter. So if you put in a 1, you get 3. What happens if you put in a 1.5? 3. And what happens if you put in a 2? 3. Okay, because that's a constant function. There's no variable. And so this is going to equal 3. So again, we have to be a little bit careful. Now is where this matters, and I'll maybe point to it. This is going to be an open circle, right? Because of the less than sign. What is this one going to be? Because this one has less than or equal to, what will happen on this dot, this circle? It'll be closed. So that's where we have to be a little bit careful on that. This will be open circle here at 3, and then closed circle at 3 on the boundaries, and then we're just connecting the middle. The only ones you have to worry about open and closed are the boundaries. Otherwise, you're just connecting, going through the dots. All right, this last one, we're going to use blue. And for this one, we need numbers that are greater than 2. So like 2, 3, and 4. What happens, again, if we put the 2 into that bottom function? So this function says 6 minus 2. So what will that give us? 4. And then what happens when we put in a 3? We get 3. And what happens when we put in a 4? We get 2. Now, once again, we do want to be careful on this boundary point. Is this boundary point going to be open or closed? And the way we figure that out is we go right back up here. Here's the boundary. So what do we think? Open or closed? Open, because there's no or equal to sign on it. So open at 2, 4, 2, 4, open circle. And then 3, 3, and 4, 2. So this is just a straight line coming down like this. And so that is what our graph will look like. Now, I will tell you, those are a little bit trickier to do on the computer. So if you need help with that, but there's usually a button to choose parabola. There's a button to choose lines or line segments, and then you usually put in like the endpoints or something like that. I know I played with it to make sure it would work, so that's how those look. Are there any questions on this? Again, the key thing is to find your boundaries and then identify if those boundaries are open circles or closed circles. That's really the important part that you're going to be working with there. And I think that that's it.